Okay, this is the team-based learning day one. We're going to be talking about the chemical senses, namely taste and smell. So here we go.
So as far as taste buds go, infants start with around 10,000 taste buds, and then by the time you're an adult, you're down to only about 3,000. And so in a lot of ways, babies are super tasters. And a lot of parents get frustrated with their kids because they are picky eaters and they don't like a lot of foods. And part of that is probably psychological, but part of it is probably also the fact that they can just taste a lot more subtleties in food than adults can. And so here's a couple shots of our kids when they're babies. Here's Soren. He's just loved shoving handfuls of sand in his mouth. He just loved the texture and the feel of the sand, and all of our kids really did that. And this is a shot of Christian trying carrots for the first time, I think, and it's real common with all of our kids. And a lot of kids, the first time they taste a new food, they just get this disgusted look on their face, and they're just completely repulsed by it. And then they keep eating it. So that's just kind of a couple shots of our little super tasters.
And so on the tongue, we have these bumps on the surface called papillae. And on the background of these slides are a type of papillae. So it's a electron micrograph picture of a tongue is actually what the back of this is, and that title slide is showing that. So these little bumps that stick up, and they give the tongue a rough texture. And most of them contain taste buds, but there's a certain type that they're called the filiform papillae that do not contain taste buds. So if you can see there under types, we've got three types of papillae. One is the filiform. These are very small. These are the ones shown in this background here. These don't have taste buds, and they're just there to provide friction on the tongue. And then we have the valate, or the circumvallate papillae, which are very large, and we only have about 7 to 12 of these on our tongue. But each of these have about 100 taste buds in them. So they form a V kind of on the back of the tongue. And then we have the fungiform papillae. These are much smaller, they're round, and much more abundant, but we have about 5 taste buds in each of these. So here's a picture of the tongue, and we can see these are the valate papillae. These are the larger ones that have around 100 taste buds each, and then you can see the fungiform papillae all throughout here. And those are the smaller ones that have less taste buds in them. And if you get a close-up view of one of these valate papillae, you can see there's lots of taste buds within one of those papillae. So the taste bud itself is kind of gourd-shaped, and in case you don't know what a gourd is, this is what it looks like here. It kind of has a larger bottom and a smaller top. And the taste pore, which would be kind of on the top up here, is where the chemical comes in, and then that opens up to the surface of the epithelium. So, and then the gustatory hairs, which are part of these gustatory cells, stick up through, and they're covered in saliva, and that's what interacts with the chemicals to stimulate these cells. We find these mainly on the tongue, but we also have taste buds on our soft palate, which is like the roof of your mouth and towards the back, towards the posterior part, inner sides of your cheeks, as well as the pharynx and the epiglottis, all on the back of your throat. You also have taste buds as well. Okay, so this figure comes directly out of the book. This is figure 15.5. I just want you to take a look at that figure in the book and be able to label the different cell types in a taste bud and all the other structures there that are being pointed at by one of the lines. So the 4, it used to be 4, but now we have accepted 5 different basic taste sensations. So sweet tastes come mainly from sugars, as you know, alcohol, some amino acids are sweet, and lead. Salty tastes come from metal, from salts, from ions. Sour tastes come from acids. Acids always taste sour to us, and bitter tastes come from things that are very basic or very alkaloid. And most drugs, most chemicals, most poisons are very, very bitter tasting. And we're about 100 times more sensitive to bitter than we are to sour. This kind of seems backwards, but actually most poisons and the medicines are bitter, and so this is good that we're very sensitive to bitter. And then the last one is called umami, which is actually kind of similar to savory, which you would think of savory with eating a nice piece of steak or something like that. This was discovered by the Japanese. It's the newest recognized taste, and this is mainly caused by amino acids. Some other tastes that we can sense are minty flavors. So when you have some spearmint gum or some peppermint gum or a candy cane that has that mint flavor, what this actually does, this is not doesn't have to do with the taste receptor. This actually stimulates cold receptors in the mouth and actually makes your brain think that your mouth is cold. And spicy foods have a similar mechanism. There's a chemical called capsaicin, which actually lowers the threshold for the stimulation of warm receptors in your mouth. So even at a normal body temperature, your mouth thinks your brain thinks that your mouth is too hot because the threshold has been lowered by this chemical. And so then this can actually spread all over your body. If capsaicin goes around your whole body, and you can feel hot and start sweating all over your whole body, so it kind of tricks you into thinking that you're hot when you're really not. And that's the origin of the spicy taste. One thing to note is this tongue map is not true. I'm sure you guys have all seen this. You taste bitter in the back, sweet in the front, salty on the sides, sour on the back sides. This is not true. All of the tongue can sense all of these tastes. So we do have some individual differences in the way people sense taste. We have people called super tasters, and they have more of those fungiform papillae, and so they're more sensitive to taste. And this is people that might have tastes that are similar to children or to babies, even into adulthood. A chemical called naringin is found in grapefruits. It's a very bitter taste. Some people taste it as bitter, and some people don't taste it at all. And this is just a genetic difference in this, and some people don't have the receptor for that. And like I mentioned before, the number of taste buds that you have declines with age. So a little bit about the neurological pathway of taste. Taste can occur in 2 different ways. One is by direct depolarization. So a good example of that is salt. When you eat something salty, sodium is released from that food, and so sodium rushes into those cells that are those gustatory cells, and that creates an action potential, just like sodium would rush into a cell, a neuron, when you're trying to have a muscle contraction. Same idea. The sodium rushes in, that creates an action potential, and that stimulates it. So you have direct depolarization by the chemical itself. You also have many others that use the second messenger system, where the chemical starts a whole long chain of events in that neuron, which leads to an action potential later on. And so after that action potential occurs, we have 3 different cranial nerves that can be stimulated depending on where the taste bud was. So the facial nerve is kind of the anterior 2/3 of the tongue, glossopharyngeal is posterior 1/3, and then your taste buds in your pharynx and in your throat are innervated by the vagus nerve, number 10. So after you get that action potential on one of these sensory neurons, it's going to go to the medulla, synapse there, and then go to the thalamus, where most of our senses integrate except for smell. And then it's going to end in the gustatory cortex of the parietal lobe, right next to the temporal lobe. So that's the pathway for taste. So we're going to move on to smell. So the olfactory epithelium is where smell occurs, and these are specialized epithelial cells, and these are found in the superior concha of the nose. So that's all up in here. So the air comes in this way, and we have these little hairs sticking down, little neurons sticking down, and that's where the sense of smell comes from. It's a very small area, it's only about 5 square centimeters, and we have about 10 to 20 million olfactory receptors, so much more sensitive to smell than we are to taste. but still nowhere near the number of receptors we have in the eyes. One thing that's interesting is you kind of need a hairpin turn to actually get the chemicals up here where they need to go to get sensed. So if you're just taking a light breath in, a lot of that air just completely misses the receptors. So when you really want to smell something, it's natural for us to take a hard sniff in. And the reason it does that is because when you do that, it kind of churns the air up, and a lot more of it interacts with the sensory receptors there, and allow you to smell it. So, and then there's, just like in the tongue, we have 3 different olfactory receptor cells, or olfactory cell types. I'm sorry. The first one is the receptor cell, and these are actually bipolar neurons, and these also get turned over pretty frequently too, not as frequently as in the mouth, but pretty frequently. About every 60 days, those cells need to be replaced, and this is very unusual for neurons. And these cells also have little hairs that stick off of cilia instead of microvilli, and these are in kind of a mucus. They're embedded in mucus, and this helps to dissolve the chemicals so they can be sensed by those neurons. And then we also have supporting cells. These surround the olfactory cells and provide some stability and shape. And then again, we have basal cells, which are the stem cells that are going to replace the olfactory receptors when they need to be replaced. Okay, so this is figure 15.2 from your book, and this is just looking at the olfactory epithelium. We're looking at the different cell types and a couple different structures there. So just go ahead and go to your book and make sure you can label all those structures, including the ones that are covered up in this diagram. Okay, so we can detect about 10,000 different odors. This is much more complex and detailed than the smell sense, and then the taste sense. And actually, most of the food that we eat, we are heavily reliant on the smell of it to actually taste its full capacity, even though that kind of doesn't make sense. But to really enjoy food to its full, you have to have your smell intact. And so when you have a cold and you're trying to eat, food is just kind of tasteless. It's not because you're anything to do with your taste receptors. It's everything to do with the fact that you can't smell the food like you normally could. And so the neurons are stimulated by different combinations of a lower number of chemicals than 10,000, probably somewhere around 7 to 50. We don't really have an answer on that. But what this requires is called volatile substances, so substances in their gaseous state, and then they dissolve in that mucus, and then they're sensed by those receptor cells. Okay, so the neurological pathway of smell is going to obviously start with the molecule binding to the membrane receptor, which is always going to start the second messenger system. In this case, there's no direct stimulation like there is sometimes with taste. And this is going to eventually open the ion channels, which leads to depolarization of the olfactory neuron. And that's going to, that depolarization of the olfactory neuron is going to stimulate neurons in the olfactory bulb, which are then going to connect right up into cranial nerve number 1. That's going to go right up into the brain. And then there's 2 separate tracks with smell. One track goes directly to the olfactory cortex of the temporal lobe, and then the other track is going to make some other connections along the way, stop in the hypothalamus, which has to do with some of the emotional responses that we have with different smells, and then stop through the limbic system, which hippocampus in particular, and this is going to connect smells with emotions, as well as certain memories. So many times we have very strong emotional ties and memories associated with certain smells that we just can't pull up other ways unless we smell an exact smell that we were smelling during that time in our lives. And then one thing we'll talk more about in class is this idea that the right nostril connects more obviously to the right side of the brain, which is our more artistic and creative side, but also our more emotional side, and that's where we're going to have more emotional responses to smells versus the left nostril, which is going to be more accurate. And what's the more logical thinking side of the brain? It's going to be more accurate differentiation between different smells. And then a condition called anosmia is the definition of that is a loss or reduction of the smell sensation. This can be a congenital thing that you're born with, and this is due to underdevelopment of those olfactory bulbs that have all the olfactory neurons in there. It can also be caused by trauma to the face. So if your cribriform plate gets crushed, um, then you can have damage to some of those neurons, some of those receptor cells, and that can make it so you can't smell. That can be temporary or permanent. Also, breathing in toxic chemicals can destroy some of those basal stem cells, and that means that no new receptor cells are able to be created. Um, Another interesting thing is zinc is very important for the smell receptors, and so if you have a deficiency, you might not be able to smell, and this can be easily corrected by supplements. Also, some of these neurological disorders we talked about last time can lead to anosmia as well, and especially some psych medications can lead to anosmia, and that's just one of the side effects of some of those medications.